In this section of the Unix lectures, we're going to go over what it takes to compile and run a C program on Unix. And I'm going to assume that you've already gotten a basic introduction to such concepts as C source code, executable file created by a compiler from C source code. You don't have to be an expert on the C language per se, but those basic ideas. What a compiler is, that it translates from source code to machine language or object code, those are presumed to be already understood in this discussion, and review necessary lectures before this if needed. Now, we're going to start off in our standard, my John Doe, your personal account, in the Lab1 directory, where all along we have had a bottles.c file available to be looked at. And as usual, go and do these commands along with me to help remember them. So we have the bottles.c file. I'm going to more that. You might do the same. See what's in there. It's a C program. Now, again, much of this may not yet be familiar to you, but the short version is that this program is going to do what is called a loop here, and will be printing out the well-known stanza, so many bottles of beer on the wall, from 99 down to 0, or down to 1 actually, the way this is written. Again, details aren't important, just the general idea that we have a C program that does this action. Now, I need to create from this source code, which of course the machine cannot execute. I can't run bottles.c. If I tried that, I'd just get an error. It isn't even a command, so it doesn't recognize that. I need to translate it to a machine language version that the computer can run. To do that, I use the GCC command. Now, this may differ from Unix system to Unix system. So if you're using this in some other context than Computer Science 101 at Cal Poly, you may find you need a command like cc instead of gcc. The typical Unix deal here, lots of different commands, subtly varying. GCC, by the way, is the GNU CC compiler. It's a standard C compiler used in a lot of courses, but there are others. This is the one we'll use here. No matter the command name, the usage is always the same. You give the command to compile and then the file you want to compile. And this will translate that C file into a machine language executable. Now, per usual with Unix, if you get no response at all, that's a good thing. The command succeeded with no need to give you any error messages. To see what happened, I'll do an ls, and I have a brand new file called, for reasons lost in antiquity, a.out. Now, what's in a.out? Oh, let's try mooring it just for fun here. See what we get. Oh, it's not a text file, so it isn't even going to try to moor it. Now, I think cat is not so picky. Let's see what happens if I do a cat. Remember, that's the one that just dumps to screen without any comment at all. Oh my god. So this is not something very readable, is it? In fact, there is a whole lot of gibberish in the middle of this, and that is not text, obviously. It's machine language. And so a.out is in fact a machine language translation. It has some textual data in there too for debugging purposes, but the guts of it is a machine language translation of the C program I just compiled. And it is an executable command. I can type a.out directly. This is a general Unix thing. If you have a file containing an executable program in machine language, you just give it as a command and it will run. So if I type a.out here, okay, I just did a little time-lapse adjustment to my account here. I was going to edit that out of the lecture, but I think I'm going to leave it in. You've seen the screen here jump suddenly, and that's because I went and did some changes. You may find this in your account as well. If you found you could not execute a.out, then the correct fix for the short term is to type /a.out, thus. That makes the shell look in the current directory for the a.out executable. And you may have your account configured in a way that doesn't do that. If you find that is the case, then just put in the / instead and ask me about fixing it later on, and we'll give a side lecture on how to repair that problem, as I just did for about 5 minutes while I paused this lecture. I've now fixed mine at least, so I was hoping yours is similarly fixed. I will do a.out, and again you can add the / if you need, and there is our Beer on the Wall song being printed out, as it should be. So we just ran an executable. Now, what about modifying a C program? Well, you use VI for that. So I'll use vi bottles.c, and let's change it to perhaps be a little less tedious, and we will, and again, you don't have to know why this is so, but I'm going to change that 99 to a 20, and that will cause only 20 verses to be printed instead of 100 of them. And so there it is. But at the same time, I'm going to accidentally remove that little semicolon up there. Yeah, a semicolon doesn't matter that much anyway, right? Saving that off, I have now done a change for the execution, but also I've introduced an error. The semicolon, in fact, does matter. And if I now compile it, I'm going to get some error output from the compiler. And this is what happens when you have compiler errors. You see the name of the file, bottles.c, and then a line number on which the error occurred. And a good rule of thumb, anytime you're dealing with compiler errors, especially confusing ones, is don't worry about the later ones, worry about the first one. Very often, confusion caused by the first will cause spurious errors further down that you don't really want to even try finding, because they'll go away automatically when the earlier error is corrected. Compilers get confused, in other words, if you do certain things, and they wind up giving you unrealistic errors later on. So the first one at least deserves attention, and it's the only one here, line 7. Sometimes the same error will give multiple messages, but it's all on line 7. Bottles is undeclared. Okay. Well, as we will find when we get into C programming a little more, that line int bottles declared a variable called bottle. Now, this illustrates another thing about the C compiler you need to be aware of. The error messages are not always that clear. Here's the line that is supposed to say, I'll have a variable of type integer called bottle. And we're looking at it and we're thinking, gee, it's right there, it declared it, and yet the error says it's not declared. Well, what the error should have said, of course, is you didn't put a semicolon at the end of the declaration, please add that. But C compilers aren't that smart. And so very often you have to kind of figure out what it's complaining about, and don't take the error message at face value. Take the line on which it occurs, usually at face value, or even there the error may be on a few lines above, but the best you can get out of an error message sometimes is just that something has baffled the compiler and you need to look more closely. I'll add that semicolon now, fixing the problem. And we'll do a GCC again, and now we successfully get a new a.out file. You know, it is kind of irritating to have my executable called this bizarre 1970s a.out name. Might be nice to be able to call it something more easily remembered, and you can do that. I'm going to repeat the compile now and add a -o option for output and the name of an executable that I'd like to have instead of a.out. Bottle, let's call it bottles. That will then be the machine language translation instead of a.out. By the way, the a.out is still there from the earlier compile. It's an out-of-date translation. I don't want to get confused by that, so I'm just going to remove the a.out. And I'll leave the bottles as my executable now. So if you don't like that name, just use the -o option and get a different one. And now I'll execute bottles. And I'll scroll up a bit to show this. As you can see, it only does the 20 verses instead of 100 of them. And so our edit has succeeded. Now, that's the essence of simple C compilation. Edit the C file, compile it, check compiler error messages, go back in, fix them till it compiles successfully, then run the executable and debug from there. There'll be more on this later, but that's a start. Now, you are going to be asked in this class, and perhaps in others, to do careful checking of the output of your C programs to be sure it is correct against model outputs, for example, that may be supplied. And to that end, I'm going to go back to the original code and change that 20 back to a 99, /20 in VI, CW for change word to 99, escape to get out of insert mode, and we're back where we were before. Be careful, of course, if I now run the bottles executable, will I see the full 100 verses or 99 verses, or will I see only 20? Stop and think about that. Coming back, what you should have come up with a conclusion of is bottles is a translation we made on the old version of the .c file. It doesn't automatically get updated to the new version of the .c file unless we do another compile. That's something not so obvious when you use an IDE in a Windows or other environment. Very often the compile is done automatically for you anytime you change the C file. But in Unix, if you want the new version of the executable, you have to redo the GCC compilation. So I will repeat the GCC, and now bottles will be updated and I can run it and get all 100 or 99 verses. I'd like to check to make sure that it's producing the right output, and what will happen in many cases is you'll be given an example file and saying, you're told this is what your output should look like. That'll require you to automatically check the content of what your program outputs versus that file. There's a web page, Testing in Unix, that you're asked to read as part of my courses at least, but I'll do a little review of that concept here as well. If you want to take what is produced by a command and save it in a file instead of having it go to screen, and this works for any program, not just for our bottles program here, you add a greater than sign after the command and then the name of a file. I'll call it my output, for instance. Everything that went to the screen now does not go to the screen. It instead goes into that file. This is called redirection in the Unix environment because I'm redirecting what would have gone to the screen into a file. Just to be sure we're clear here, let me more my output and let's see what's in there. There it is, the output that would have been on the screen, all 100 verses of it. That then lets me save the output to see if it compares properly. The model that I was given was the song file, in fact, which is correct output. Let's see if it matches or not. Now I can always eyeball it, but that can be a real pain with a long output and probably inaccurate. So Unix provides a file, or a program, diff, that checks two files to see what the differences between them are. You give the command diff and then the two files you want to compare. So there are some differences here. I wonder what happened. Let's look at song and see what's in there. Oh, that's right. Remember, I changed it to Coke earlier in a prior lecture. It's still that way. And so it's showing me differences between those two files. Let's take a look at what those were again, just to see how they look. So, let's see. Yeah, this isn't going to be too good an example. And we run the command, and if nothing is shown, as is the case here, that indicates that those two files match each other. So my output and song are identical. No news is good news. Now, what if we wanted to make a difference occur actually? Let's go in and just edit my output just to see what happens if diff has a problem. We'll take out 99 bottles of beer on the first verse here, and let's change this dot to a comma and see what happens. So now I'm going to rerun that diff command, and we see this. Diff output can be a little nasty to read. Ignore these symbols with 1A2 or 6C7. Their rationale is out of date and they're really just noise. The lines you want to look for are those that have a greater than or a less than in the front of them. A greater than line is telling you that this line occurs in the second file, in song, but not in the first. A less than is showing you a line that occurs in the first file, but not in the second. So this is showing you the difference between the comma and the period. Actually, I'm sorry, I misspoke. This is showing you that 99 bottles of beer is missing from my output. These two here are showing you that 98 bottles of beer with a comma is present in my output, but with a period is present in song. Sometimes the difference is quite subtle. A good example of why you want diff, by the way. You might have missed that if you just eyeballed it, the two files to see if they were the same. So, when you're checking for accurate output, you want a clean diff. And if there are differences, you check to see which file they're in and where you made the mistake accordingly. By the way, it is possible if a file has input, which ours really doesn't, but if one did, to get the input from a standard file. And that would be done by writing, again, if we had input, bottles less than input. And in the file input, you can name the file anything you like, of course, you do a VI session, and in text you put whatever you would have typed at the keyboard for the program, and it will read from that file as a player piano almost, automatically running the program based on the content of that file instead of taking it from the keyboard. You can combine the two too. You can do less than input and greater than output, and the whole thing runs automatically from standard input to a standard output, which you can then diff. So you'll be doing a fair amount of this to check accuracy of programs, and you want to have redirection both from and to files in your toolkit, so to speak. Now that's it for a very brief introduction to compilation, C compilation in Unix, and we'll have more detailed discussion of this later on.